So just a little short introduction. My name is Sydney. I'm a graduate student here at the University of Arizona in the GIST program. And I just wanted to take a quick moment to say thank you for taking time out of your day to join me and learn about my research project for the semester. And with that, we will begin. So I wanted to focus on the shift of tornado genesis or tornado events in the United States, specifically looking at three study areas being the Great Plains, Tornado Alley, and Dixie Alley, and kind of how that shift is moving towards the away from the traditional Tornado Alley and towards Dixie Alley. Okay, so first off, what is a tornado? Based on the definition from the National Weather Service, a tornado is a narrow, violently rotating column of air that extends from a thunderstorm to the ground. These will vary based on geographic location. They obviously don't occur everywhere as frequently. And they also, more than likely not, will stem from a thunderstorm. Now, these thunderstorms don't have to be the most severe. They can also spin up from weaker thunderstorms as well. And here we can see a little time series map. On the bottom right, you can see as time is ticking away, more tornadoes pop up. And the colors do represent on the EF scale magnitude. So you can kind of see they're very centralized and they most often occur kind of in that Great Plains down in the south. But there are some tornadoes that occur out towards the west and the northwest, and then even in places like Maine. And then for this study, we're going to focus on a couple different time periods. We are going to look at two equal time periods for 36 years, one being from 1950 to 1986, and then the second being from 1987, and then going until 2022. And then we'll specifically look at the year 2021 for some of our models later on. So just kind of a quick overview of how you can recognize a tornado. There's on the left, you can see there's four pictures. And these are all kind of what it'll look like on radar. So the top left is going to be what you traditionally see. The one next to that on the right is going to be your velocity, so your wind speeds. The brighter the colors is going to be the faster that wind is going, and then the color is representing your direction. So red's going to be away from your weather station, green's going to be towards, and you can kind of see when they get those tight couplets like that next to each other, that will then be the rotation. Your bottom left is going to be your debris. So it's measuring, that is specifically measuring the likeness of the atmosphere. So anything unlike the atmosphere, any debris that's going to come up from a tornado is going to show up blue, and you can kind of see how it's in a circular shape. And then the bottom right is going to be your differential reflectivity. And this is showing horizontal width versus vertical height. So it's going to see negative numbers for something that's taller than it is wider, which is how you're going to see a tornado. And those are all taken at the exact same time from the exact same storm. And on the right, that's kind of a visual representation of what that would look like in real life. So that's kind of the structure of your storm. Now, there's a couple things we can look at for this analysis. The variables for tornado formation most often occur from wind shear, which is going to be how your winds vary at different heights. You're going to want faster moving winds aloft and then slower moving wind speeds down below. Instability is self-explanatory, so you get the more stable the air is, the less likely you're going to have a thunderstorm and then even less likely to have a tornado. And you're also going to want surface level warm air, and you're going to want cold air aloft. And then lastly, you're going to want moisture. So we can collect data on the variables. So for wind shear, we can look at storm relative helicity. Instability is going to be convective available potential energy, or CAPE. And then your surface level warm air and cold air aloft is going to be temperature, and moisture is obviously going to be dew point. And for this analysis, I wanted to look at how and where tornadoes are forming currently, kind of with that time series map, and then where will tornadoes form in the future. So these are our three study areas. The light yellow and tan color is going to be the Great Plains. The red area is Tornado Alley, and then your green is Dixie Alley. And there is quite a bit of overlap between the Great Plains and Tornado Alley. The Great Plains is more of a regional definition that comes from NOAA and the NWS, and Tornado Alley is kind of a location and area that got defined by a geographical phenomenon like tornadoes. So there is quite a bit of overlap between those, and that's why the red will look two different colors, but it is all the same area, and the study will also include those bottom areas that are not a part of the Great Plains, which can add to the variability, and you'll see that those numbers will vary quite differently due to those two areas on the bottom. And this is a quick overview of kind of the methods that went into the process to get this analysis together. And if we kind of break it down, the first thing we looked at was our time series map, and then we just looked at our study areas map. So we had to download quite a bit of data for this. We'll download our CMIP6 data. That is going to be our future predictions, and we'll get to that in a little bit. But that's just data from dew point temperature that we'll use to predict the tornado genesis for the future. The NCEI NARR RDA data, which is a mouthful, that's going to be our current observed variables. So we're going to take that from 2021, and those come in the form of monthly means. And then we have a couple feature services that are available online through Esri, and that's the software that we're going to use. So we'll use a US counties and states and layer, and then we can kind of use that to define some of our maps later on and use that for some analysis. And then lastly, we have our climate division shapefile from NOAA that kind of assisted in that study areas map that we saw previously. So to get the time series map, we just took one of the feature services available from Esri, also in conjunction with FEMA. They track all the tornadoes from 1950 until 2023. And we just kind of enable our time elements, add some animations, add our legend, and that gave us our time series map. With our climate divisions, we took, obviously it's not going to be like what you saw, but they're in smaller chunks. So we kind of select those in conjunction with the US states feature service, and we combine those into one area to make those 3 study areas. And then you'll see in a minute, we're going to have a study areas counts map. That is going to take those 3 study areas, and we're going to find where the tornadoes intersect with those, where they cross into those areas, and then we'll count those. We'll count those for both the total and then both of our 36-year time periods. And then we're going to use our NARR data. So that's going to be our current 2021 data. That's the furthest and most current that they have. So those come in monthly means. So that means every variable that we have, and we have our 4, there will be 12 individual files and 12 individual measurements. So we do have to do a little bit to kind of combine those, which is you'll see the mosaic to new raster and then the different bands. But once we have all that straightened out, we then put it into our modeler, and we get a risk assessment for 2021. And that's going to be the observed environment. So it's really crucial to understand that it's not a prediction. That's what environment actually occurred for that year. And then a very similar process will occur to get our last 2 models. We're going to do a 2021 risk assessment check. So basically, we're going to use our CMIP6 data, that prediction data for 2021. The data set came out in 2015, so that data is projecting and predicting what 2021 variables would perform like. So we're going to use that, and we're going to use our CAPE and helicity variables from 2021 to make a check model, basically. And we're going to run that against our 2021 actual observed model, and we're going to see how similar they are. And that way we can verify that when we do use this data for 2030, it can be fairly accurate. And the reason we have to use the 2021 CAPE and helicity for both the check model and our 2030 prediction is because nobody really does any prediction data for CAPE and helicity. And then we can do all of these models will put out a high risk region, and you'll see those a little bit later on. And so they'll kind of predict and show where that environment is most favorable and where the risk is the highest. So then we're going to look at where those overlap our study area. So we can, we'll look at the cells, and kind of with a raster, they'll have pixels or cells, and we'll make sure that we can look at where they overlap as far as the total cells in that study area. So first, we're going to look at that total tornado incidence. As you can see, the Great Plains has the most from 1950 until 2022. This isn't partly due because it is so great of an area compared to the other 2. The Great Plains is over 718,000 square miles. Tornado Alley is a little bit over 400,000 square miles. And then Dixie Alley comes in at 274,000 square miles. So quite a big difference there, and that could partly cause this to look so skewed in favor of the Great Plains. But as we can see, when we break it down by those 2 36-year periods, it shows quite a different story. So the Great Plains actually had a 0.09% decrease. Tornado Alley had a 0.17% increase. But the real difference here is Dixie Alley, which has a 24.7% increase. So at first glance, it may not have looked like Dixie Alley had a significance in the tornado genesis environment, but as you can see, it's the increase that we're looking at, and this shows that there is quite a significant shift over the last 36 years. And this is a representation of what these rasters for these variables look like. And then to put this into our model, we do have to go ahead and classify in criteria 1 to 5, 5 being your most at risk, and then the 36 to 74, that first interval is going to be your lowest risk. And the numbers are going to be highlighted in green. That is going to be your threshold for more favorable tornado environments. So at 150 meters squared per second squared, that's going to be where you're going to start getting tornadoes. And then the same thing goes for Cape. And this, again, same thing goes for temperature. And this is in Celsius, so this isn't going to be 31 degrees Fahrenheit. So just keep that in mind when you're looking. These aren't as low as what you think. And then same for dew point. And we can put these all together to create our risk assessment. So this is using our prediction data for 2021. So this is going to be those dew point and temperature for the prediction from 2015. So this shows that this gray area is going to be highest risk region. And you can see visually there is quite a bit of overlap with Dixie Alley. It's an 8% overlap for the Great Plains, 23% for Tornado Alley, and Dixie Alley has 43%. And we can see those numbers here at the bottom. So then if we're going to compare this and make sure that our prediction data is going to be good for our 2030 prediction, we can compare this directly to what actually occurred. So this is the current data for 2021. This is the actual environment for that year, which is really crucial. Last model we saw was a prediction. This is actually what happened. They do have a 40% overlap between those two highest risk regions in gray. So we can see that our prediction was a little bit on the milder side. This actually does have a bigger, higher risk region and an even further overlap in Dixie Alley. And the Great Plains had 7% overlap. Tornado Alley was at 20%. And then Dixie Alley was at a whopping 59%. For this, their model used was a middle of the road model. So it's not their most severe that they put out, but it's also not their least severe. And this study did not want to sacrifice specificity for sensitivity. And using a more severe model could account for the difference in just being 40% overlap. And now we can look at our 2030 tornado risk assessment. This is going to look very, very similar to the 2021 prediction model. Obviously, using CAPE and helicity as the same variables is going to make this look a little bit similar, which is a limitation of this study. But due to the fact that nobody does use the prediction for CAPE and helicity, it's a little tricky to kind of get that environment to look different. But we can see that it's very similar. You still see the greatest overlap with Dixie Alley. And for the Great Plains, it's at 9%. So it does go up a little bit. Tornado Alley's at 24%. And Dixie Alley's at 39%. So we see that the prediction a little bit was underestimated and that there is still a significant shift from 2021. And then in 2030, that trend will continue. And we do see that shift from Tornado Alley and also the Great Plains. And it's shifting from more rural areas to more dense and underprepared areas. Historically, you think Tornado Alley, it's going to give it away. There's a lot of tornadoes there. So they've built the infrastructure. They've gotten used to how that is to live there and the engineering and the community resilience. Dixie Alley doesn't have that. And it's a fairly new shift for them. And it looks like it's going to continue. So that area will definitely have to take precautions and kind of understand what's to coming, and that trend is not going to go away. And I think this goes to show that you can use the suitability modeler and GIS to predict future weather, not just for tornado events, but it could also be generalized for other weather phenomenon as well. Thank you.